All right, good afternoon, everybody. My name is Al Wegener. I'm the CTO and founder of a 6-year-old startup called Samplify. We're in Campbell, California. And we've heard several talks over the last 2 days about what a problem I/O is for supercomputing, especially as exascale is approaching. Instead of making pipes bigger, Samplify has a different proposition. What if you could make the operands smaller? We're all familiar with, we're carrying around iPhones. I left mine back at my desk. That's full of video, audio, and image compression. It's interesting to think, what if you could get somewhere between 3-to-1 and 10-to-1 compression of HPC data? And what I'll be presenting today is some of the results that we've done with a few of our partners in seismic, in multiphysics, in climate, where they're getting 3-to-1 to 10-to-1 smaller files. Some customers use the compression technology for making RAM 3 to 4 times larger, 3 to 4 times faster. Some people use it for flash. Some people use it to expand their InfiniBand links by a factor of 3. And some people use it for just making the disk drives faster. We just heard Brent Gorda talk about the fast forward challenge, where the DOE would like the data to go 10 to 100 times faster. So let's talk a little bit about how compression could possibly solve that problem. So in a nutshell, the problem is HPC is I/O bound. Memory, disk, and networking. 40 gigabits and 56 gigabits sounds like a fast interface, but not when you have to send 100 terabytes back and forth. We think the solution is numerical encoding to make the HPC operands, because those could either be floats or integers, smaller. When it basically, wherever you have computations still occur in the natural native format that the processor does. Could be IEEE 754, 32-bit, 64-bit numbers, could be 8-bit, 16-bit, 32-bit ints, but in our experience, the typical operand for most of HPC is 32-bit floats. I'll present 3 areas where we have results already, and we're writing papers with some of these folks for SC13 and ISC13. And the results are between 3-to-1 and 10-to-1. And I think that's a pretty compelling value prop. Even if there may be some skeptics in the room that lossy compression could possibly work for your data set, hopefully these results that we have from some name brand application areas will hopefully convince you to try our software. The software is shipping now, and these numbers may also surprise some people. On a single x86 core, we can support 250 megabytes a second of encode or decode, and that is independent of where the knob is set. If the setting is at 3-to-1 or 10-to-1, it runs at the same speed. Interesting for some people in the room, if there's anybody here from Intel or NVIDIA or IBM, we have this available as an IP block, and you can imagine what a flexible numerical compressor might mean for handsets in the future. One of the problems that the handset folks have is reference frames for video, and those are taking up 2/3 to 3/4 of the available bandwidth. Is there a question?
Yeah, I didn't understand what you meant by encoding rate.
Encoding rate means how fast can we compress and decompress data. For instance, if you had, let's say, a gigabyte of RAM that stores floats, and that could store 3 gigabytes of RAM, but you need to encode it when you're reading the compressed data from RAM into your processor, and you need to encode it when it leaves the processor. So in other words, compressed data is stored in RAM, compressed data goes across networks, compressed data is stored in disk, but then when it comes onto the chip has a first step, which is to decode the data, then to process it as it always did with your application, CFD, seismic, climate, and then when you're finished, whatever the results are, your time step is advanced or whatever, you then write that data out and compress it.
What's the ratio? What I didn't understand what was the ratio?
The ratio is user selected and between 3-to-1 and 10-to-1. So the memory wall problem has been mentioned in several other presentations today. And there's an interesting graph that I put together a year ago for a multi-core developer conference to basically show you that as the core number of cores went from 1 to 2 to 4, going up to 6 and 12 now for Intel processors, Intel has done something interesting. They've added more and more memory controllers, but unfortunately they haven't added as many memory controllers as they've added cores. So the I/O per core has actually either stayed the same or gone down. The trend is much more obvious for GPUs. The latest Kepler processor has 1536 cores. So there's been a tripling of the number of floating point units in GPUs, but the I/O has gone from 384 pins to only 512 pins. So they've only increased the I/O by 50%. So the I/O per processor has definitely gone down. Our idea is, what if you made the numerical operand smaller? One other thing we'd like to point out is, as power becomes a problem, the picojoules that John Schaff talked about yesterday, picojoules to move data versus picojoules to compute on data. The power in today's data centers and HPC centers, in many cases, could be DDR and disk driven, not CPU driven. There was one gentleman yesterday who mentioned that the cost of HPC systems, maybe 25 to 30% of it, is accounted just by the DDR. And there's a similar trend for where the power is being spent. So imagine if the data that you send out of a CPU has been compressed by a factor of 3. So the DDR memory needs to store 1/3 less data. The number of bytes going across the network is 3 times smaller. And what goes to disk is now getting there 3 times faster. And the most important thing, that this is where we'd like to talk a little bit about our existing results. The computational results remain the same. The computational results remain the same, not by our judgment, but by the judgment of geophysicists in the case of seismic processing, climate scientists in the case of climate, and the guys that are doing the multi-physics experiments. So APAX is a universal numerical encoder. It's kind of a bold statement, but that's what we set out to invent. 8-bit, 16-bit, 32-bit ints, 32-bit, 64-bit floats. Put those in and we compress them. The place where APAX really helps HPC is if you have an I/O bottleneck. If you are running, let's say, the Linpack benchmark and you're getting 70 or 80% of peak CPU utilization, we're probably not going to help you that much. But I think most of us in the room realize that Linpack is not as useful as it used to be. That's saying it kindly. Many of the HPC scientists that we talk to all over the country and all over the world, they have huge I/O bottlenecks, and their CPUs in many cases are maybe 20% busy. So I took an example here where if your CPU is busy 10% of the time and waiting 90% of the time, what would 2-to-1 compression do to the time to results? And although this is a little bit hand-wavy, a little bit marketing, your 90% becomes 45%. So 45% plus 10% compute, the computation time remains the same, is 55%. So 2-to-1 compression means that you're getting your results 1.8x times faster. Similarly, if you can get to 4-to-1 compression, your 90% gets chopped into 1/4, and then which is 22.5%, and then the extra 10% for computation. Now your CPUs are actually running 3 times more often. So you should, in theory, get your results 3 times faster. Not everybody has this 10-to-1 ratio, but I'd say that many people in the room might have a 5-to-1 ratio. So let's do a little thought experiment. I'm going to keep it on this slide here. Imagine that somebody sends you a 1 megabyte data set and said, please make this 3 times smaller. And I want to make sure that my results stay the same. How would you go about doing that? There's a couple of things to think about. What does it mean for the results to stay the same? If you do climate simulations, typically you have 50 to 100 different parameters you want to run. There's some inherent statistical variability just in the starting conditions and the state variables that you insert. So there's variation in the output. It's not always clear what the same answers mean. But there's a couple things that you can be sure of. When you encode and decode the data, there is a residual. There may be a difference. It may be small, it may be large. But what you want to know is the difference between those two certainly should be zero mean. So you haven't added any offset to the signal. It's nice if the standard deviation of the input is the same as the standard deviation of the decompressed signal. You'd like the relative error and the absolute error to be as small as possible. And basically, you'd like this residual, the difference between the input and the decoded data, to be spectrally white. And what that means is that from DC to Nyquist, if there's any signal processing folks in the room, it means that you have white noise. And if you can control the amplitude of that white noise with increasing compression ratio, that can be modeled as simply a decrease in the signal-to-noise ratio. Now, the interesting thing is that I've asked many climate scientists, well, how good is your data? And they'll say, well, it's 32 bits good. It's 23-bit mantissa, and it's great, and therefore I could only use lossless compression. And then I ask them a question. Okay, well, you've got a temperature variable here that's taken up a gigabyte. How was that temperature acquired? And they'll say, well, it came from a sensor. I say, well, okay, how good is the sensor? And they'll say, oh, it's really good. It's a 1/10 of a degree C. And I'll say, well, what's the hottest temperature that was ever recorded on the surface of the Earth? And typically they don't know. It's 57 degrees C, somewhere in the Sahara Desert. What's the coldest temperature ever recorded? It's in the Arctic, or it's on the Kamchatka Peninsula, minus 90 degrees C. So if you do the math on from minus 90 to plus 60 in a 1/10 of a degree increment, you could store that pretty easily in a 16-bit int. So when they tell me that their 32-bit float has perfect bits, I don't believe them. But that's me, one guy, saying this doesn't work. The whole purpose of this next tool, the Apex Profiler, is to give scientists like yourselves insight into your data that you probably don't even know. One thing you probably don't know, some of you may know, what's the spectrum of your input signal? Another thing that you don't know is, well, what's my rate distortion curve? If I were to use this APAX compression technology, what is the trade-off between the achievable compression ratio and the signal quality? So this upper left-hand graph gives you the answer to that. We have a curve here which shows on the y-axis the Pearson's correlation coefficient. If anybody's had a intro statistics class, you got 1 million samples of X, 1 million samples of Y. How similar are they? Please give me a number from -1 to +1. So the place where the profiler software, which you give the data that you'd like to compress, the profiler software says, well, we think at 5 nines of quality, 0.99999, as the similarity between the input data set and what you get back, is a good place to start. And for this particular example, which came from a climate variable, we're running at 6:1. This is what the Apex Profiler recommends as the compression ratio. And at that level of 6:1, you get 5 nines of quality. The second screen here is 18 different metrics. I mentioned some of these before. The mean and the standard deviation of the input data, the decoded data, decompressed data, and the residual, the difference between the input and the decoded. We also have an FFT, or a power spectral density graph, down here. And here you see that the signal peak is at -67 dB. These are tiny little floating point numbers. The signal floor is at -113 dB. So you've got about 50 dB dynamic range of your input. Most users don't know what the dynamic range of their signal is. Now, the most important thing that I can leave you with today is this. When I mentioned that the residual spectrum is flat, it's like white noise from DC to Nyquist. That's really important because that's what guarantees that the signal is zero mean, that the residual is zero mean, and that it's as small as possible. What as small as possible means in this case, at 6:1 compression, the energy of the residual is 21 dB below the smallest frequency component of your input signal. What that means in layman's terms is you don't have 23 mantissa bits in this example. You probably have 10 or 12 mantissa bits. And our residual that we introduce is riding at maybe 15 or 16 mantissa bits below that. So the residual is small, and it's below the level of noise that's inherent in the data itself. This last graph is the residual histogram. This thing is important because it typically will show you something like this, a Poisson distribution, and 95%, 2 sigma, 95% of the differences have magnitude, in this case, 6.6 times 10 to the -7th. Is that good? Is that bad? Well, the input signals in this case went from ±7 to 10 to the -4th. So 10 to the minus 7th, that's the residual, the error. 10 to the minus 4th, we have a factor of 3 orders of magnitude here. So these are tiny little numbers compared to the min and the max of the data itself. So let's bump up a level here. The purpose of the profiler is to let scientists like yourselves know how much compression can I achieve on my data set. How much can I achieve on my data set? When you're done with the profiler, you say, I'll take it, and it creates a JSON file, which goes into a library. It says, okay, next time I do a precipitation, pr.dat, variable in my climate simulation, I'm going to use 6 to 1. Then you run this profiler on however many variables you might have. The multi-physics guys we work with, they had 8 variables. Climate guys had 100 variables. So you profile your variables, a one-time process. You create your library of compression settings, and then that's what you use when it comes to encode your data when you're doing 100 terabytes. All right, here's a block diagram of the encoder. Really complicated. We have an attenuator. We have a redundancy remover, which you can think of as just doing time domain differences. And then we have a joint exponent encoder. There's a technique called block floating point encoding, where you take 4 samples, find the maximum, and encode all 4 samples into the number of bits that the maximum needs. That's it. So this block diagram, being as simple as it is an explanation for why on a single x86 core you can run at 250 megabytes a second, encode or decode. The algorithm is symmetric, so decode is a little bit faster than encode, but not by a lot. Okay, let me get to some results that we've achieved with our customers. In seismic, there's lots of different signals. You basically, let's say you're dragging a ship and a bunch of 10-kilometer streamers across the Gulf of Mexico. You're prospecting for 6 weeks. You're collecting 2 terabytes a day. After the 6 weeks, you go with your couple hundred terabytes. You go back to your supercomputing center, and you've got all these traces. The way seismic prospecting works is they have an air gun dragging behind the ship. It fires every 10 seconds, and then you record acoustic signals for 10 seconds after that. These things are called traces. The first thing that happens when the data goes back to the supercomputer is that you do a demultiple process. You're trying to get some of the noise out. So you're averaging typically 4 or 8 traces together in floating point format, and then you save those demultipled traces. Those are then the input to another process called reverse time migration, which creates a 3D image of the Earth after 3 to 6 months of iteration and looking at it with geophysicists. Once you start producing from an oil field, you have all these pressure, temperature, density, porosity, reflectivity measurements for drilling, and there we've gotten between 6 to 1 and 12 to 1 compression, depending on the accuracy of your metric. So with each of these 3 examples I'm going to give you, I'll kind of introduce the results, how much compression did we get, and then say, what does the profiler tell us about this? So this happens to be one of those traces. Imagine you're one of the sono buoys in the back there, and you've just recorded data for 10 seconds. And this is what the spectrum of the signal looked like. It's pretty wide band. It certainly has a center frequency here at 1/4 the Nyquist frequency. Here's our friend, the residual. It's, in this case, about 7 dB below this very lowest frequency component, which I think is pretty safe. You'll see that here, in this case, the rate distortion curve drops off pretty quickly at around 6 to 1. We recommend that we operate here at around 4.6 to 1 compression, and that preserves this 5 nines level of quality. Here's some multi-physics examples. This is, we're working with the guys at the National Ignition Facility. They're trying to heat up a little pellet of deuterium to get it to fuse. And they do that by getting it into a plasma. They fire 192 lasers into the plasma, and then they go see what happens. It's really hard to instrument that, and it costs a lot of money just to fire up the machine. So they're much happier doing 8,000 to 12,000 CPU years of simulations, either at Livermore or at Argonne. And they have a big problem with all this data. So they sent us these variables. This is not all of them. But here we can basically show you, here's the spectrum of the signal, and then at different compression ratios, 2 to 1 should give you better quality than 3 to 1. So you would expect that the residual level should eventually increase. Now, the physicists had no idea, is this a good margin? You know, do I need 21 dB? Do I need 50 dB of margin here? Well, it turned out for these guys, they could get, this one is the reflected laser intensity, they could get 4-to-1 compression here. So that's this level right here. For the best performing one, the density, they were better than 6-to-1. So here's the profiler signal on, this is the input laser energy. So here we recommended a compression ratio of 3.75 to 1 to maintain our 5 nines of quality here. Again, for those of you that know a little bit about compression, the best spectrum you can have to compress looks like this one, where you have all of your energy is at low frequencies. So that means that the signal is oversampled. If you put it on a plot, you'd see a bunch of little dots, and you just connect the dots very easily. You might have 100 dots per cycle of your main waveform. That's a really easy signal to compress. Harder to compress is something that looks like this, where you have kind of a wide spectrum, and you've got a big blob of energy, and it's kind of bumpy. But look, here's our residual, flat as can be, and that's because of the way the algorithm works. And in this case, our residuals are at 1 times 10 to the minus 4th. The input signal is 7 times 10 to the minus 2. So again, we have about a factor of 700 between the errors, the residuals, and the input range. Let me skip one. That's it. I guess that was it. All right. Yeah, here's the third one, the climate. For the climate data, here's a really nice looking rate distortion curve. It's pretty much flat, so you could probably go well past 10 to 1 in this case, but we're recommending 8.5 to 1 because the profiler stops at 10 to 1. So here you see our favorite spectrum, the fact that you have all the energy in the low frequencies, meaning that this signal is highly oversampled and therefore can be compressed by quite a lot and still maintain that 5 nines of accuracy. Again, the error is 6 times 10 to the minus 2, 0.06, whereas the input range is from 229 to 276. All right, I wrote a paper which was accepted for a presentation at the Data Compression, IEEE Data Compression Conference in Snowbird, Utah. I'll be presenting that on the 21st of March. If any of you guys will attend the Data Compression Conference, it's mostly academic, but a couple of industrial folks like myself. Here we show that this works for the data sets, the data types that I mentioned. We have the suffix here of the file, -8, I8, I16, I32. This is integer bits. We have some of the CT images. We work with GE Healthcare to do compression of their 16-bit X-ray samples that are going across a slip ring at many gigabits per second. So they're using our FPGA version. The majority of the data comes from the 32-bit floats and 64-bit floats. And they're on the entire ensemble of 25 files. We got better than 6.5 to 1 compression with 4 nines and a 3 of correlation. All right, for the Intel and NVIDIA types, this is where we would like to go someday. If this compression stuff works, we can get started at 250 megabytes a second per core using this in software. The kinds of speeds that the storage servers require, they're putting 6 and 12 core Sandy bridges and Ivy bridges into some of these RAID controllers. So there's lots of MIPS available for doing compression and decompression in the storage array itself. The biggest bang for the buck is if you compress at the source and the destination. Sorry, compress at the source when it's leaving the chip and decompress at the destination when it's coming into the chip. And what we'd like to do eventually is to put our little Apex encoder decoder into a hardware IP block. Those of you that don't know chips, 1/10 of a millimeter square fits under a bond pad. So you've seen the ring of bond pads that go around a chip. That's where the I/O comes from. You could also have 3 through silicon vias. We would be a little dot around that area. We would like to be integrated into the memory controller, so that whenever you do a write, the write is a special kind of, let's say, mem copy, and it knows that it's going from on-chip to off-chip memory, and therefore it automatically compresses. When it's coming back into memory, it says, oh, it's coming from a compressed area of RAM, it's on the heap, and then it comes back and it automatically gets decompressed. The CPU, the SIMD unit, the GPU FP units, they don't know any different. They're just crunching floats like they always did. Okay, our CEO, Alan Evans, is in the back there. He put together this nice little ROI analysis to show you what you can do if you're doing something like Amazon EC2. Anybody tried Amazon EC2? I tried it at a show, and the room was full of 70 people, and 20 minutes after they started their little interactive thing where everybody was trying it, 60 people had left. It was really hard. I don't mean to denigrate Amazon EC2, but at least a year ago, I wasn't ready for prime time. But this number here, 10 cents a CPU hour. Has anybody heard that number before for the smallest instance of Amazon EC2? One of the problems with EC2 and with cloud is, well, you got to get the data there. If you're an HPC scientist and somebody sent you a terabyte disk drive, you can email that, or you can FedEx that disk drive to Amazon EC2, but they're going to charge you $80 for just receiving it, and they're going to charge you $2.50 per hour to unload the disk drive. And if your disk drive is typically the 50 megabytes a second, it's going to take a while. They're going to charge you maybe a couple $100 just to get the data off the drive and onto your EC2 instance. So what if you could upload that data in the time that it took you to FedEx them a disk drive? How much would that save you? The baseline system we start with is basically we have about 7 terabytes of data, 7.5 terabytes of data, and we only have 2.5 terabytes of RAM, and therefore our data set won't fit. So in this instance, it's going to take us 44 days on the EC2 server, and it'll cost $50,000. The next example, where we just compress the data, here we go. We fit the 7.5 terabytes of encoded trace data into 1.8 terabytes of DDR memory. And there we assume a compression ratio of 4 to 1. And when you come down here, we've gone from 44 days to 10 days. That's ROI. But wait, we're not done. So in this case, we can compress the data on the fly if Intel or NVIDIA were to take us up on our value prop. That now we're running, instead of at 250 megabytes a second, maybe we're running at a gig or 2 gigabytes a second. We're integrated into the memory controller. Now all of a sudden, I/O is not nearly a problem. Now it's only $5,000 and it only takes 4.5 days. So almost finished. To summarize, what we're proposing is really, we're giving you a software knob, a software upgrade that promises, can't guarantee, but will promise to increase your RAM, your network speed, and your disk drive capacity and bandwidth by a factor of between 2x and 10x. The profiler software that we have is available today. You can go to profiler.samplify.com, upload your data set, and you'll get to see one of these profiler graphs for the data that you just uploaded. I think we're limiting it to 10 megabytes. So if it doesn't come back after a while, then maybe the file was too big. But in any case, here's my contact information. And we are looking to collaborate with all kinds of organizations. We've started working with NCSA, RN Labs, Lawrence Livermore, NCAR. But I've contacted people yesterday and today to try to start new collaborations. We'd like people to use our software. It's very inexpensive, and it gives you an awful lot of bang for the buck. We also think that for file system folks, like Brent, there could be value in putting this into disk drive controllers and subsystems to sell it as software that basically is a new way to reduce the I/O and memory wall of supercomputing. Thanks very much.